What you doing, Andy Palm?
I'm trying to get my golden nugget out of my safe, but I can't remember the 4-digit code. How many codes do I need to try?
We can use permutations to figure out how many.
Today's video is our first in-depth math video, and today we're going to talk about permutations. We're going to answer, what is a permutation? Why are permutations important? And how do we count the number of permutations of a set? Let's start with what is a permutation. A permutation is a particular arrangement of a set of things. Order matters here. In an earlier video, we went over how many ways can we arrange 3 candies. For 3 candies, there were 6 different arrangements or permutations. Let's show a few examples. Here's one possible arrangement or permutation. Here's another one. And finally, here's a third. There's 6 of these, because there are 3 ways we could choose the first candy, and then once we've chosen one, 2 ways to choose the second. Once we've chosen that one, there's only 1 way to choose the third. So, the number of permutations of a set of 3 candies is 3 times 2 times 1 equals 6 permutations. While we're using candy here, the objects we're arranging can actually be anything. In fact, 3,000 years ago, the Chinese were arranging broken and unbroken lines in a book called the I Ching for spiritual guidance. Later, in the year 718, an Arab mathematician, Al-Khalil, used permutations to list all possible words with and without vowels in the Arabic language. You may be wondering, so what? Well, Al-Khalil's work with permutations influenced a later Arab mathematician, Al-Kindi, and Al-Kindi developed a method of code breaking that was used by the Allies in World War II to break several of the Axis's codes. So, we can all be thankful for Al-Khalil and permutations. Maybe a little less glamorous, but if you're watching this on a cell phone, you're using permutations too. Permutations are used in something called error correcting codes that your phone uses to help you watch YouTube when you don't have great signal. So we can all be thankful for that too. There are several things we can do with permutations, but one thing we can do is count them, and that's what we're going to be focusing on in this video. We saw that for a set of 3 items, there were 6 ways to arrange them, or 6 permutations. Let's draw a square, a star, and a triangle and prove this to ourselves. So we'll start with our square, then our star, and then our triangle. This is permutation number 1. Now we could have square, triangle, star. It's the second permutation. We can have triangle, square, star, third permutation. Triangle, star, square, fourth permutation. Star, triangle, square, fifth permutation. And finally, star, square, triangle, sixth permutation. These are all the possible ways we can arrange this set of 3 items of a square, a star, and a triangle. Let's look at why there are 6 ways we can do this. It's the same thing as with the candies. So for each possible position number 1, 2, and 3, we have to choose an item. Do we choose a square or do we choose a star? Here I will draw a circle to represent our set of 3 items, and I'll put inside of it a square, a star, and a triangle. Here are our 3 positions. So we haven't picked anything out of our set yet, but let's pick a triangle. Now, for the first position, there were 3 things in our set, 3 things we could possibly pick. So 3 possible choices. We've picked a triangle, so now it's gone from the set. For the second item, we can either pick a square or a star. Let's pick a square. There were 2 possible choices here. And now that we've picked our square, that's gone. So for the third position in our permutation or arrangement, there's only 1 item left in our set, and that's our star, so we have to pick that. And so to count the number of possible arrangements, we multiply the possibilities in each position. So we have 3 times 2 times 1, 6 possible arrangements. 1, 2, 3, 4, 5, 6. If we had a set with 4 items, there would be 4 times 3 times 2 times 1, 24 possible arrangements or permutations. Now let's work out how many permutations there would be for a certain number of items, not just 3 or 4, up to 8. For this, we'll draw a table. In the rightmost column of our table, we'll show the number of items. In the leftmost column, we'll show our work, multiplying the number of possibilities for each position together, and in the middle column, we'll show our answer. Something that's kind of crazy to me is how quickly the number of permutations increase relative to the size of the set. Going back to our candies, for our 3 candies, there were only 6 ways to arrange them. But if we had 8 different candies, there would be 40,320 possible ways to arrange them. That's wild. Now we're going to see what we've done so far and see if we can find a pattern. We're going to see if we can figure out the number of permutations or arrangements for any number of items. First, let's make sure we understand our table here. In the rightmost column, we have our number of items. 3 in this column is like when we were arranging our 3 candies. In the middle column, we have the number of ways we can arrange the number of items in the rightmost column. Like I said earlier, the middle column is our answer. But the leftmost column is what I want to draw our attention to, because it shows how we got our answer. For a set of 4 items, there are 24 ways of arranging them, because there are 4 ways to pick the first item, 3 ways to pick the second item, 2 ways to pick the third item, and only 1 way to pick the 4th item. If we look at the table as a whole, we may notice that there's a lot of repeated work. For example, in each permutation, 3 through 8, we multiply 3 times 2 times 1. If we already know 3 times 2 times 1 is 6, we can just multiply 6 times 4 to get the number of permutations for a set of 4 items. Say we already did the work to figure out the number of permutations for a set of 7 items. It would be really great if we could avoid doing that work when figuring out the number of permutations for a set of 8 items. And we can. We can multiply 5,040 by 8 to get 40,320. For each number in the number of items column, the corresponding number of permutations is equal to that number multiplied by the previous number of permutations in the middle column. The case of 1 is special. There's only 1 way to arrange a set with 1 item. Now I'm going to show you how that pattern looks using what's called math syntax. And what I mean by that is how that pattern looks in a math textbook. We'll use some symbols, but don't let your eyes glaze over. The symbols are just shorthand for the pattern that we've already talked about. All right, so here's how this would look in a math textbook. Let's ignore the left-hand side of these symbols for now and focus on the first line. We see 1 when n equals 1. N here is a placeholder for the number of items. Remember, we're trying to figure out the number of permutations for any number. So n is a placeholder for any number. We said earlier that there's only one way to arrange a set with one item. So the number of permutations when n is 1 is equal to 1. The second line is more interesting. When the number of items n is not 1, how many permutations do we have? Using our pattern from before, we have the number of items multiplied by the number of permutations of the previous number of items. The word perms here is a word to describe the thing we're creating with all these symbols. A function. A function is something that takes an input and produces an output. I think of a function as a little machine on a conveyor belt. Here's some little gears. And there's our little machine. In our case, the number of items goes in on one side of the belt, and the machine spits out the number of permutations on the other side. We called our function perms, but we could have called it anything. The name of our function does not affect its operation. Let's work out a few examples here on paper to make sure we understand how our function is working. So let's start with 1. That's our simplest case. Say perms of 1. The parentheses here mean apply this function. So it means run our little machine, put our input into the conveyor belt and run our little machine. So perms of 1 is just 1. There's only one way to arrange a set with one item. I'll show you. There's only one way to arrange that pink candy. Let's go to our more interesting case. We have perms of 2 is equal to n, which is 2 here, times perms of n minus 1, 2 minus 1 here, is perms of 1. And we said from before that perms of 1 is 1. So we have 2 times perms of 1, which we said was 1, equals 2 times 1 equals 2. Okay, great. Perms of 3 is equal to n, which is 3 here, times perms of n minus 1, so 3 minus 1, which is 2. Okay, great. Well, what's perms of 2? Perms of 2 is equal to 2 times perms of 2 minus 1. And we're back to where we were before. 2 minus 1 is 1. Perms of 1 is just 1 because we said it was. And so here we have 3 times 2 times 1. So perms of 3 is 3 times 2 times 1, 6. Let's do one last example here. Perms of 4. Perms of 4 is equal to n, which is 4 here, times perms of n minus 1. So perms of 4 minus 1 is 3. Perms of 4 minus 1, 3. Perms of 3 is equal to n. N is now 3 because we're inside of another little machine, perms of 3. 3 times perms of n minus 1. And remember, we're inside of another little machine here. So 3 minus 1 is 2, which is equal to 2 times perms 2 minus 1, perms of 1, which is equal to 1. So for perms of 4, we have 4 times 3 times 2 times 1 equals 24. All right, so that's it for counting the number of permutations of a set of n items. I hope you enjoyed learning about this math concept and find it interesting, if even just as a puzzle. If you did, please consider subscribing for future math videos.
And food.